In this video, we present Prime, a unified framework for recovering latent physics from standard robot sensing. Prime jointly estimates robot motion, contact interactions, and inertial parameters within a physically consistent optimization framework, and we validate it on diverse legged robots, including humanoids. Over the past decades, robot capabilities have evolved dramatically, from whole-body control to today's general-purpose control policies. At the same time, robots are equipped with increasingly rich sensing, including IMUs, joint sensors, vision, force, and tactile. Yet, these measurements remain fragmented and do not directly provide a uniform understanding of the underlying physics. This motivates our question: can we jointly recover motion, contact, and inertia from standard robot sensing? Here is the problem formulation. Given a set of robot sensor measurements, we formulate the maximized procedure problem that have the robot state trajectory, physical inertial parameters, and contact forces composed as uncertain variables. We then optimize to find the most probable solution, thus provide the joint estimates of all three latent variables. The question is why joint estimation actually helps. The key is that these variables are not independent. They are coupled by physics. Robot dynamics describe how motion evolves under inertial properties, while contact dynamics govern interactions with the environment through non-penetration, friction, and complementarity. These physical constraints naturally connect motion, inertia, and contact, allowing information to propagate across both variables and across time. In our MAP formulation, this coupling is encoded as dynamics factor together with measurement factors and prior factors, resulting in physically consistent estimates of all three latent variables. One major challenge of solving this MAP efficiently using gradient-based methods is that the contact dynamics factors are not differentiable. To mitigate this problem, we leverage a smoothed surrogate of the complementarity conditioned contact dynamics. As we know, rigid complementarity is physically accurate but is non-smooth and difficult to optimize. We therefore introduce a smooth log barrier version that provides well-defined gradients while preserving the behavior of rigid contact. This makes the entire optimization differentiable and significantly improves convergence. We first evaluate Prime on both quadruped and humanoid robots. Despite their very different morphologies and dynamics, the same estimation framework accurately recovers motion, inertia, and contact using standard robot sensing. Next, we will show quantitative results for inertial identification, followed by contact and force estimation. As a representative example, we attach a 4.6 kilo payload to the Unitary Go2. Without any prior knowledge of this change, Prime accurately identifies new inertial parameters directly from dynamic locomotion data. In particular, it successfully recovers both the added mass and the shifted center of mass, demonstrating robust inertial identification in real-world experiments. Finally, we ask a simple question: does joint estimation lead to better contact estimation? The answer is yes. Compared against guangzhous from force plate, Prime achieves lower force estimation error and lower optimization cost once the inertial parameters are jointly identified. Similarly, better performance is achieved with estimated contact instead of fixed contact guangzhous. This illustrates the key idea of Prime. By jointly estimating motion, inertia, and contact, each component improves the others through shared physics consistency. To conclude, Prime provides a unified framework for jointly estimating robot motion, inertial parameters, and contact interactions from standard robot sensing. We believe that recovering these latent physical quantities leads to better robot model, more physically consistent state estimation for planning and control, and richer data for downstream learning. Looking ahead, we plan to extend this framework beyond locomotion to manipulation and whole-body interactions, and leverage physics-aware annotations to support future physics AI and foundation models. Thank you so much.